Lesson 5, solubility factors. We're still on solution. So the objectives for this unit will be to identify the factors or the things that will affect the solubility of a substance. For instance, temperature, pressure, volume, things like that. And the question you're going to be able to answer is, why do some things dissolve and others do not? So going with our lesson notes here, solubility factors, we're going to start with factor 1. And I have everything filled out for you already, so I'd like you to just fill it in, come back and listen. So like dissolves like for factor 1. That's a good way to remember this. Nonpolar solutes will dissolve in nonpolar solvents, okay, because they're alike, nonpolar and nonpolar. And polar solutes will dissolve in polar solvents because they are alike. Now the exception is your ionic solute. Because they have charges, the only way that they are going to dissolve is in a polar solvent to allow the charges to be attracted to the polar ends of the polar solvent. Okay, so we got to talk about charges there. Nonpolar solvents don't have partial charges. Okay, when we talked about that in bonding unit, the nonpolar solvents have an electronegativity difference of 0 to 0.5, virtually negligible. So there are no partial charges there to allow for the ions to break up. So ionic solutes are your ionic compounds, a metal and a nonmetal. Okay, so if we look, nonpolar solute will dissolve in a nonpolar solvent, but it will not dissolve in a polar solvent. So we call that insoluble. All right, you're not going to say unsoluble, it is insoluble. Then we have a polar solute, okay, and that's the solid or the liquid that we are pouring or trying to mix into the solvent that does the dissolving. Polar will not dissolve in a nonpolar solvent, so it is insoluble, and then polar will dissolve in a polar, and we say that is soluble. Okay, ionic solutes, again, we have to talk about charges there. The only way that it is going to dissolve is if we use a polar solvent. Water is polar. This is very important that you remember this, okay? And I told you guys this during the bonding unit. Water is a universal solvent. Most substances are polar, okay? So that's why a lot of things do dissolve in water. But other things that do not, like oil is nonpolar. This is why it does not dissolve in water. Okay, they are not alike. So here we talk about a styrofoam demonstration. I will try to do it in class if I have enough acetone. But what happens here is when we have water and we pour that into maybe a styrofoam cup or pour it on top of, you know, one of those styrofoam little peanut things out of packaging, styrofoam is nonpolar. And when we try to mix that with polar, what's going to happen is the styrofoam is going to stay intact. Okay, it's actually going to float in the water. Now, if I take acetone and pour that on top of a piece of styrofoam, the styrofoam will start to dissolve. Very similar to the use of acetone polish removers on the acrylic nails. Okay, salons will not use acetone unless they want to take the acrylic nails off and destroy them, okay, because it will eat at the acrylic because the acrylic nail is nonpolar and acetone is a nonpolar solvent, okay? So factor 2, temperature. For solids, as temperature increases, solubility is going to increase. So if you think about this, all right, when you heat something up, it allows for things to dissolve much easier. Okay, maybe not necessarily quicker. It will happen quicker, but not always. But it is going to make it easier for it to dissolve. Okay, so if you remember, table G will always be there to help you and to help you remember what gases and which ones are gases and which ones are solids. Gases slope downward, so we can look at how temperature affects it that way. Solids slope upward, so we'll look at how temperature affects solubility in that sense for solids. Okay, for most gases, all right, as temperature increases, solubility is going to decrease, and that's why the slope is downward. Okay, here's a prime example. When you heat soda, carbonation is lost. It goes flat. Think about it. Not many people like to drink warm soda, but if it does sit in a car on a hot day, it will go flat. Okay, the carbonation will be lost, even though it might still be under pressure. You're increasing the temperature of it as well, so it's going to make the carbonation release much quicker. Okay, so another example, another great example of this would be a fish tank. For those of you who have fish tanks, fish tank example. So if you listen to me, because I'm not going to write it all down, O2, oxygen, will dissolve in H2O, okay, and this is a gas, O2 gas, will dissolve in H2O at a specific temperature, which allows the fish to breathe underwater, okay, it allows them to survive. Now, if we heat the water up, now it's going to disallow or not allow the O2 to dissolve because the solubility is going to go down. The temperature goes up. Now that oxygen will not dissolve. There will be less oxygen in the water, so the fish will die. That's why it's important to keep the temperature of your fish tank consistent. Okay, as soon as it starts to get warm, you might see those fish dying. Now, tropical fish can withstand an increased temperature or less oxygen in their water. So therefore, they can survive in warmer waters. But otherwise, like goldfish, need to be at like a room temperature water. All right, and then factor 3 is pressure, which really applies to gases. Now, there's little to no effect for solid or liquid solutes. If you think about it, if I put a liquid solute under pressure, what's really going to happen? The volume is going to change. But as far as solubility, you're not doing anything. You're putting pressure on it, and it's not going to increase your ability to dissolve. Okay, same thing for a solid. You're just going to crush it, basically. So for gases, very specific. Okay, gases dissolved in liquids. This is how it works. As pressure increases, the volume will go down of the liquid, and the solubility will increase. It will force those gas molecules into the solute, which is generally going to be water, okay? But it will force those gas molecules into the water and cause them to dissolve. So if we can recall, we can change the volume of gases. We can by putting them under pressure. And the reason is because gas is forced into less space per liquid, so it dissolves more. It's forced. All right, so here's a can of soda example. When packaged, soda is pressurized, so the CO2 will dissolve in the liquid. When the can is opened, the pressure is let out, the pressure decreases in the can, and the particles are released, and you get carbonation. Now, there is a space between the actual soda, the liquid soda, and the top of the can. Okay, so that's why it reduces the volume of the liquid, but there's still space because that gas is in there, all right, and partially dissolved in there as well. So here's a cute little cartoon for some of you who have so many things going on. We got a boombox in the back. We have a student listening to an iPod, a computer, work in front of him. The TV is blaring. And he or she, we can't tell, is saying to themselves, I'm finding it difficult to concentrate, but I'm not sure why. All right, we're going to actually talk about concentration, so I thought it was a little cute. But anyway, those of you guys who are distracted, maybe you should limit your distractions. Okay, so that will finalize lesson 6, and we'll talk about using table F, which is solubility, next lesson.